The sun has a far side. Half of it is hidden from us at all times, and every 27 days, what was hidden rotates into view. Today, on May 10th, 2026, something rotated in that nobody on Earth was watching for. It announced itself with an M5.7 flare, strong enough to take out high-frequency radio across the entire daylit hemisphere. It launched a coronal mass ejection, and it's not in any forecast database yet, because the region didn't exist as far as Earth-based observation was concerned until 3 days ago. So the question isn't whether today's flare was bad. The question is what this region was doing during the 2 weeks we couldn't see it. Stay until the end, because the answer changes everything about the next 14 days. At 13:19 Universal Time on Sunday, May 10th, 2026, the sun did something forecasters specifically said wasn't going to happen today. A region we couldn't see, a region that had spent the last 2 weeks completely hidden from every Earth-based observatory and every Earth-orbiting satellite, decided to announce its presence. And the way it announced itself was with a flare strong enough to take out high-frequency radio communication across the entire sunlit hemisphere of our planet for tens of minutes. The official classification is M5.7. That's a moderate class flare on the X-ray scale, the kind of event that happens roughly 20 to 30 times during the most active part of a solar cycle. By itself, an M5.7 is not a once-in-a-lifetime event. It's not even a once-in-a-month event. But the M5.7 that erupted today is different from every other M-class flare in 2026 because of where it came from. And once you understand where it came from, the entire story changes. The flare began at 13:19 Universal Time. It peaked at 13:39. It ended at 14:02. That's a 43-minute event from start to finish. The peak X-ray flux exceeded the M5 threshold, which automatically triggers an R2 moderate radio blackout warning from the National Oceanic and Atmospheric Administration's Space Weather Prediction Center. NOAA issued the alert, code SUMXM5, serial number 316, at 14:14 Universal Time. The blackout itself was already in progress by then. Pilots flying transatlantic routes, ham radio operators in the Pacific, mariners on high-frequency networks, anyone trying to communicate in the high-frequency band on the daylit side of the Earth experienced minutes of degraded or completely lost signal. That part is normal. That part is what an M5.7 flare does to Earth's ionosphere when it points its X-rays at us. What's not normal is the radio fingerprint the flare left behind. About 10 minutes into the eruption, at 13:29 Universal Time, monitoring stations around the world picked up something called a Type 2 radio emission. NOAA logged it as alert code ALTTP2, serial number 1484. The estimated velocity of the shock front producing that emission was 650 kilometers per second. To put that into language a human can actually feel, that's a wave of compressed solar material moving outward through the sun's atmosphere at roughly 1.5 million miles per hour. A Type 2 emission is the radio signature of a shockwave. It's the cosmic equivalent of a sonic boom, and it's the unmistakable fingerprint of a coronal mass ejection being launched into space. A coronal mass ejection is a billion-ton cloud of magnetized plasma that the sun occasionally hurls off its surface. When one of those clouds is aimed at Earth, it causes geomagnetic storms, auroras at unusual latitudes, satellite failures, and in extreme cases, power grid disturbances. The May 10th event launched one of these clouds. We can hear it leaving. We can measure it leaving. The shockwave is real, the plasma is real, and the energy is real. About 5 minutes after the Type 2 emission was detected, at 13:34 Universal Time, a third signature appeared. This one is called a 10-centimeter radio burst, also known as a 10 flare. NOAA logged it as code SUM10R, serial number 911. It peaked at 550 solar flux units. That number doesn't mean much without context, so here's the context. The Penticton Observatory in British Columbia measures the sun's microwave emission every day at noon, and that measurement provides the global baseline for solar radioactivity. The most recent Penticton noon flux was 122 solar flux units. The May 10th burst peaked at 550. That's 4.5 times the daily baseline. And the burst lasted 15 minutes, which by 10 flare standards is a long, sustained, energetic event. 10 flares are produced by superheated electrons spiraling around magnetic field lines in the flaring region, and they correlate strongly with the broadband radio noise that degrades satellite communications and global positioning system receivers. If you were using single-frequency civilian global positioning system equipment in the sunlit hemisphere during those 15 minutes, you may have noticed your position briefly drift, jitter, or temporarily lose accuracy. Most people wouldn't have noticed. The systems that did notice are the ones that depend on centimeter-level precision, and they will have logged it. So we have a flare, we have a shockwave, we have a 10 flare. We have a confirmed launch of a coronal mass ejection. And here's where the story gets interesting, because the coronal mass ejection is not pointed at Earth. It's pointed 30 degrees away from us, off into the open solar system, where it will dissipate harmlessly over the next several days. The reason it's not pointed at us is the entire reason this video exists. And it's the reason that when you finish watching this, you're going to look at the sun a little differently for the next 2 weeks. The location of this flare, the heliographic coordinates that NOAA published, are north 18 east 65. Translated out of orbital geometry, that means the eruption happened just below the sun's equator, 65 degrees east of the line that connects the Earth to the center of the sun. From Earth's vantage point, the sun rotates from east to west, so a region at East 65 is just barely visible. It's right at the edge of the eastern limb. It's a region that, 3 days ago, we couldn't see at all. And the question of what that region was doing during the 2 weeks before we saw it, that's where this story stops being about today's flare and starts being about something much bigger. Before we get to the hidden region, you need to know about the regions we can see. NOAA tracks active regions on the sun the same way meteorologists track tropical cyclones. Each region gets a number when it crosses a threshold of magnetic complexity, and once numbered, it gets monitored daily. The numbers reset every 10,000, so right now, we're in the 4,400s. On May 10th, NOAA was tracking 6 numbered active regions on the sun's visible disk. The biggest one is active region 4432. It sits at north 14, west 56, which means it's well into the western half of the visible disk and rotating off the western limb over the next 4 or 5 days. AR 4432 is what solar physicists call a magnetically complex group. Its magnetic class is beta gamma, which means it has both positive and negative polarity sunspots intermixed in ways that make magnetic reconnection the engine of solar flares especially likely. Its Macintosh class is EKI. That's a code that describes the size, structure, and spot distribution of the group, and EKI is among the more flare-productive classifications. The region currently has 28 sunspots. Its total spot area is 430 millionths of the solar disk, which places it in the upper tier of regions for the entire current solar cycle. It is, at this moment, the most threatening visible region on the sun. NOAA assigns daily probabilities to each active region for producing flares of various classes. AR4 432's probabilities for May 10th are 70% for C class, 25% for M class, and 5% for X class. That 5% is the number you should pay attention to. X-class flares are 10 times stronger than M-class. They're the kind of flares that produce the most violent space weather. A 5% daily probability means that if you waited 20 days, AR4432 would, on average, produce one X-class flare. The region has been on the visible disk for roughly 12 days. It hasn't produced an X-class yet. Whether that means it's never going to, or whether it's overdue, depends entirely on how you read the magnetic structure. The honest answer is nobody knows, and the SWPC forecast discussion, issued at 12:30 Universal Time, today specifically called out AR4432 as the primary reason for the elevated R3 blackout probabilities through May 12th. The other 5 regions are smaller and less threatening. There's AR4436 at North 19 East 54, a beta-class region with 6 spots and 150 millionths of area. There's AR4435 at North 23 West 16, an alpha-class region with a single spot. There's AR4434 at North 14 West 32, a region so quiet it's currently spotless and has 0 flare probability assigned. There's AR4433 in the Southern Hemisphere, a beta-class region with 12 small spots. And there's AR4431 at South 16 West 76, a single-spot alpha region rotating off the western limb. Combined with AR4432, these are the 6 regions NOAA was actively monitoring this morning. Now look at the location of the flare again. The flare came from North 18 East 65. The easternmost numbered region on the visible disk is AR4436 at East 54. The flare happened 11 degrees further east than the easternmost numbered region, which means it didn't come from any of the 6 numbered regions. It came from a region that, as of the morning of May 10th, was not yet visible to NOAA's classification system. It came from something the official forecast didn't know existed. That's the moment in the story where you have to stop and absorb what just happened. NOAA's 12:30 Universal Time forecast, published less than an hour before the flare, listed AR4432 as the primary R3 driver. The forecast wasn't wrong. AR4432 does have a 5% X-class probability. The forecast was simply incomplete because the region that actually erupted at 1319 wasn't in the catalog. The forecast couldn't have warned about it. The forecast couldn't have predicted it. The forecast was constructed using every region the sun had revealed to us, and the sun was hiding one. Here's how the sun hides things from us. The sun is a rotating sphere. From Earth, we only ever see one half of it at a time. The other half, the far side, is invisible to direct optical observation from any Earth-based telescope or any spacecraft positioned near Earth. We can see the far side indirectly, using a technique called helioseismic imaging, which detects sunspot groups by measuring the way solar pressure waves travel through the sun's interior. Helioseismic imaging works, but it has significant limitations. It has a roughly 24-hour latency. It can't reliably detect small or short-lived regions. It produces low-resolution maps that show where active regions exist, but it can't tell you their magnetic complexity, their spot count, or their flare history. We have the Stereo A spacecraft, which orbits ahead of Earth and gives us a partial view of one section of the far side, but its coverage is geometric and incomplete. The bottom line is that for any given 2-week stretch, there's roughly half of the sun whose detailed activity we are essentially guessing about. The region that produced today's flare spent approximately April 22nd through May 6th on the far side. That's 14 days of growth, of magnetic emergence, of complexity development, of flare activity that we either missed entirely or saw only the faint helioseismic shadow of. When the region rotated around the eastern limb on May 7th, it emerged into our view already in motion. We didn't watch it grow. We didn't see its first flare. We saw its first publicly observed flare on May 7th at 1420 Universal Time. An M2.6 event from coordinates north 18 East 90. North 18 East 90 means the region was literally right on the edge of the eastern limb at the moment of that first observation. We were seeing only the very edge of whatever this region had become during its time hidden from us. 3 days later, on May 10th, the same region had rotated another 25 degrees into view. By the time it produced today's M5.7 flare, we could see roughly half of its structure, and what we could see produced an event more than twice as energetic as what we saw on May 7th. The flare doubled in strength as the region rotated into better visibility. The question that should be making the hair stand up on the back of your neck is, was the region growing during those 3 days, or were we just seeing more of what it already was? Because if it was already at full complexity, and we were just seeing more of it, then we know what we're dealing with. If it was actively growing, then we have no idea what it's going to do over the next 2 weeks. The reason the flare didn't cause a major space weather event for Earth comes down to one factor, and that factor is angle. When a flare erupts at the center of the sun's visible disk, what solar physicists call sub-Earth or central meridian, its X-rays, its energetic particles, and its coronal mass ejection are all aimed directly at us. A central meridian flare of a given strength produces the strongest possible Earth impact. The same flare at the limb produces a much weaker Earth impact because the geometry is wrong. Most of the energy gets directed sideways, into space, away from us. The May 10th flare happened at 65 degrees east of central meridian. That's a very large angle. 65 degrees of separation means most of the flare's directional output went 30 degrees northeast of the sub-Earth line. The X-rays still reached Earth, because X-rays travel in all directions and propagate at the speed of light, so the radio blackout was real. But the coronal mass ejection, the slower-moving plasma cloud that takes 1 to 4 days to cross the 93 million miles between the Sun and the Earth, was launched in a direction where, if you traced its trajectory forward through space, it would never intersect Earth's orbit. NOAA's 1230 Universal Time Forecast discussion stated explicitly, and I'm quoting now, "No Earth-directed coronal mass ejections were observed in available coronagraph imagery." That sentence was written before the flare. The afternoon update, which has not yet been issued at the time of this analysis, will reflect today's eruption. But the geometry hasn't changed. A coronal mass ejection from north 18 east 65 is not an Earth-directed coronal mass ejection. It's a near miss by design. You might be wondering, if it's not Earth-directed, why are we even talking about it? Why is this video an hour long? Why does any of this matter if today's flare didn't actually do anything to Earth? The answer is the same answer to a question you've probably never thought to ask, which is, how does the sun rotate? The sun completes one full rotation, as observed from Earth, in roughly 27 days. That's called a Carrington rotation, named after Richard Carrington, the 19th century English astronomer who first measured solar rotation by tracking sunspots across the disk. 27 days for one full rotation means each region of the sun's surface takes about 13.5 days to traverse the visible disk from the eastern limb to the western limb. That, in turn, means a region currently sitting at east 65 degrees will reach the central meridian, directly facing Earth, in approximately 1 week. From there, it will remain in geo-effective position, meaning capable of producing an Earth-impacting flare or coronal mass ejection for the following 10 to 14 days. The region that produced the M5.7 this morning is going to be pointed directly at us starting around May 17th, give or take a day. It's going to remain in the bullseye until late May. And whatever this region does during that 2-week window, every flare, every coronal mass ejection, every shockwave it launches, will be aimed directly at the planet you are sitting on right now. Today's flare is not the climax of the story. Today's flare is the prologue. It's the moment when a previously unknown chapter of Solar Cycle 25 walked onto the visible side of the stage and announced itself with a moderate strength eruption. And the question I want you sitting with for the rest of this video is, what does this region do for an encore? The current state of Earth's space weather environment, the part that's measurable right now, is almost surreally calm given what just happened on the Sun. The geomagnetic field is quiet. The KP index, which measures global geomagnetic disturbance on a scale of 0 to 9, has been bouncing around between 1 and 2 for the past 24 hours. The forecast through May 12th keeps KP below G1 storm threshold the entire time. Solar wind speed has been declining from around 500 kilometers per second yesterday to around 400 kilometers per second now. The interplanetary magnetic field strength is in the 2 to 4 nanotesla range, which is the cosmic equivalent of a gentle breeze. The B's component, which determines how efficiently solar wind energy couples into Earth's magnetosphere, is sitting near neutral. There is no aurora forecast for mid-latitudes. There is no geomagnetic storm in progress. There is no active radiation event. The greater than 10 mega-electron-volt proton flux is at background levels. There's no proton storm. There's no satellite radiation emergency. Everything is quiet. Right up until you remember that the sun just launched something violent, and the only reason it didn't hit us is geometry, and the geometry is going to change. Before we get to what the new region might do, we need to talk about the region we already know about, because it's not done yet. AR4432 is rotating off the western limb, but it's not gone. It still has roughly 4 to 5 days of geo-effective position remaining before it crosses the western limb and disappears from our view. During those remaining days, it carries a 5% daily X-class probability. 5% doesn't sound like much, but when you're talking about a region with an Icky-Macintosh classification and a beta-gamma magnetic structure, 5% is what NOAA conservatively assigns. The historical X-class production rate for regions of this complexity is closer to 10 or 15% per 24-hour window. NOAA's forecast is on the cautious side because over-forecasting strong events undermines public trust. The actual likelihood of AR4432 producing an X-class flare in its remaining time on the visible disk is meaningfully higher than the published 5%. And here's the structural irony of where AR4432 sits right now. The region is at West 56. That's still within the geo-effective range. A coronal mass ejection from West 56 can still glance off the edge of Earth's magnetosphere, depending on the trajectory and angular width of the ejection. Some of the most surprising geomagnetic storms in the historical record have come from regions at western longitudes, because the spiral structure of the sun's magnetic field, the so-called Parker spiral, named after astrophysicist Eugene Parker, connects more efficiently with Earth from the western side of the sun than from the eastern side. A flare from AR4432 over the next 4 days could absolutely impact Earth. The probability is not 0. It might not even be small. So here's the picture. On the western limb, a known monster with 28 sunspots and a 5% X-class daily probability is rotating away from Earth, carrying its remaining geo-effective potential into the final days before it disappears. On the eastern limb, a previously unknown region just announced itself with an M5.7 flare, a shockwave at 650 kilometers per second, and a 4.5 times baseline 10 flare. Neither region is currently aimed at Earth. Both regions are simultaneously capable of producing major space weather, and the sun is rotating, which means within the next week, the new region will swing into the bullseye while AR4432 simultaneously rotates out of it. There's going to be a brief overlap in mid-May, where both regions are simultaneously visible and both are within geo-effective range, and the threat profile during that window is genuinely uncertain. What you have here is the kind of setup that solar physicists call a dual-source threat geometry, and it's the kind of pattern that produces some of the most underestimated space weather events in the historical record. Forecasters have a tendency to focus on whichever region is currently dominant. They published their morning forecast highlighting AR4432 as the primary R3 driver, and that forecast was already obsolete by lunchtime because a different region produced the day's biggest event. When the new region rotates into a more central position over the coming week, the forecast attention will shift to it. AR4432 will recede in the analysis, and there's a real risk that AR4432 produces a major event during its final geo-effective days, after the operational attention has shifted to the new arrival, and the warning lead time gets compressed because nobody was watching the right region anymore. This isn't a conspiracy. It's not a hidden agenda. It's a structural property of how forecast attention naturally allocates itself across multiple simultaneous threats. The people at SWPC are extraordinarily good at what they do, and they know exactly how this kind of dual source week unfolds. But the public-facing communication of that complexity is harder to maintain than the public-facing communication of a single dominant region. So if you watch the news over the next 2 weeks and you see a story about a major flare from a region you've never heard of, you'll know which region it came from. Or you'll know it was AR4432 having one final tantrum on its way out the door. Either is plausible. Both are possible. And both are genuinely, materially capable of producing an Earth-directed event during a window that hasn't started yet. The question of which one matters more, the known wildcard on the western limb, or the unknown rising region on the eastern limb, that question is going to be answered by whichever one fires first, and there's no way to know in advance. There's no way to forecast which region's magnetic structure will reach instability first. The sun keeps its own clock, and we just watch. Let's go back to the new region for a moment and ask the question I promised you we'd get to, which is, what was this region doing during its 14 days on the far side? The honest answer is, we don't fully know, but we have enough indirect evidence to build a careful picture, and the picture isn't reassuring. Helioseismic far-side imaging is the technique we use to indirectly observe the sun's hidden hemisphere. The technique was developed in the late 1990s by a research group led by Charles Lindsay and Doug Braun, building on theoretical work by physicists going back to the 1970s. The basic idea is that the sun's interior is full of acoustic waves. These waves propagate through the entire body of the sun and carry information about the magnetic and density structure of every region they pass through. Sunspots disturb the propagation of these waves in characteristic ways, and by measuring the disturbance pattern as observed from Earth's side, you can infer where sunspot groups exist on the far side. The technique works. It's been validated thousands of times by waiting for far side regions to rotate around to the visible side and confirming that the helioseismic detection was correct. But the technique has real limitations. It produces low-resolution images. It can't tell you a region's magnetic class or its sunspot count. It can detect that a region exists and roughly how big it is, but it can't tell you how dangerous it is. It misses small or short-lived regions completely. It has a roughly 24-hour latency between observation and image production. And critically, for the question of what this specific region was doing, it doesn't catalog flares. There is no record of which far-side flares this region produced before it rotated into our view. We can sometimes detect very large far-side eruptions through their effects on the heliosphere, through the trajectory of coronal mass ejections that pass stereo A, through proton events that reach interplanetary monitoring satellites. But for a moderate-class flare from a region we weren't specifically watching, the event is essentially undocumented. So the data we have on this region's 2 weeks of hidden activity consists of helioseismic images showing that something existed at roughly the right location, plus the May 7th M 2.6 flare we saw on the lim's edge, plus the May 10th M 5.7 flare we saw today. From those data points, we can construct 3 different stories that all fit the available evidence equally well, and each story has very different implications for what happens next. Story number 1 is what I'll call routine emergence. Under this interpretation, the region is a typical mid-cycle bipolar group that grew on the far side over the course of its passage, reached approximately full complexity, and is now near the peak of its productive lifetime. The escalation we've seen from M 2.6 to M 5.7 over 3 days reflects only the geometric advantage of seeing more of the region as it rotates into view, not actual ongoing growth. Under this story, today's M 5.7 represents close to the region's ceiling. The next 2 weeks will produce additional moderate flares as the region rotates across the disk, but nothing dramatically larger than what we've already seen. This is the most common outcome for late cycle solar cycle 25 regions, and it's the modal scenario. Story number 2 is what I'll call active growth. Under this interpretation, the region's magnetic complexity is genuinely still increasing. New magnetic flux is emerging from the convection zone underneath the photosphere. The escalation from M 2.6 to M 5.7 is partly geometric and partly real. The region hasn't reached its peak. As more flux emerges over the next several days, the region could develop into a beta-gamma-delta classification, the most flare-productive complexity class, capable of producing X-class events. If that happens during the central meridian window in mid to late May, we would have an Earth-directed X-class flare from a region that, 2 weeks earlier, didn't appear in any forecast. This story is less likely than story number 1, but it's not unlikely. And the consequences of this story being correct are an order of magnitude more significant than the consequences of story 1 being correct. Story number 3 is what I'll call the late cycle far side surge. This one requires some context. Solar Cycle 25 was officially predicted by NOAA's Solar Cycle 25 prediction panel in 2019 to be a relatively weak cycle, peaking at around 115 sunspots on the smoothed monthly count. That prediction has been spectacularly wrong. The actual smoothed monthly maximum, reached in mid-2024, came in at approximately 215. That's nearly double the predicted peak. The cycle has also stayed elevated longer than predicted. We are currently in what should be the early declining phase, but activity remains high enough that the declining phase has been more like a sustained plateau than a decline. Under story number 3, the new region we just observed is not an isolated event, but rather the latest in a continuing pattern of unexpected high activity from regions that grew during their far-side passages. If this pattern is real, we should expect to see additional unfamiliar regions rotating into Earth view over the coming several solar rotations, each one providing surprises that the official forecasts couldn't have predicted because the regions weren't yet in the catalog. Under this story, the May 10th flare is a warning shot for a continued period of elevated, unforecasted activity that could persist for months. 3 stories, same evidence, wildly different implications. There is no way to distinguish between them based on what we know today. Distinguishing between them will require watching what the region does over the next 48 to 72 hours, and what other regions do over the following several solar rotations. We are, in other words, watching real-time science unfold with consequences for the planet we live on, and we don't get to skip to the end of the book. There are several anomalies about today's event that don't fit cleanly into any of the 3 stories, and they deserve their own examination, because they're the kind of details that tend to get smoothed over in standard reporting and that often matter more than the headline numbers. The first anomaly is what I'll call the geometry versus magnitude mismatch. Flares at high heliographic angles, meaning flares far from central meridian, generally produce weaker Earth-side effects than flares of equivalent magnitude near the center of the disk. The reason has to do with how X-ray emission angles into Earth's atmosphere. A flare at the center of the disk shines its X-rays directly down at us. A flare at 65 degrees east of center shines its X-rays at a steep slant angle. The slant angle reduces the efficiency of ionospheric coupling, meaning the X-rays interact with Earth's upper atmosphere at a less effective geometry. The same magnitude of X-ray flux produces a smaller observed blackout. This is why the M5.7 producing a confirmed R2 blackout is unusual. M5.7 flares at the central meridian routinely produce R2 blackouts. M5.7 flares at 65 east should be producing weaker blackouts, possibly only R1. The fact that today's event triggered a clean R2 designation suggests the flare was either at the high end of its magnitude classification, meaning it was almost an M6, or it had unusually strong broadband radio output that compensated for the geometric inefficiency. The 550 solar flux unit 10 flare argues for the second interpretation. This was a flare with unusually energetic radio production. That may be a coincidence, or it may be telling us something about the specific magnetic configuration of the new region. Regions with delta spot complexity, the most flare-productive variant of beta gamma, tend to produce extra energetic radio bursts. We don't yet know if the new region has delta spot structure, because we haven't seen enough of it. But the radio signature of today's flare is consistent with the kind of structure that would make stories 2 or 3 more probable than story 1. The second anomaly is the brevity of the May 7th M2.6 flare. When the region first appeared on the limb edge at east 90 degrees on May 7th, it produced an M2.6. 3 days later, with the region now 25 degrees further into our view, it produced an M5.7. The energy ratio between these two flares is roughly 10:1. An M5.7 releases approximately 10 times the energy of an M2.6. The temporal spacing is 73 hours. If we plot the energy escalation over time, the trend is steeply upward. And here's the part that should make you pause. The trend has not yet leveled off. We have not yet observed a sequence of declining flares from this region. The two flares we've seen are both stronger than each predecessor. That's an escalating pattern, not a decaying one. Stable, mature regions produce decaying flare sequences, where each subsequent flare is smaller than the one before it, as the available magnetic energy gets discharged. Growing regions produce escalating sequences, where each subsequent flare is larger than the one before it, as new magnetic complexity emerges. The pattern we've observed for the new region is consistent with growth, not decay, which pushes us slightly away from story 1 and slightly towards stories 2 or 3. The third anomaly is what's not visible in the coronagraph imagery. A flare with a type 2 radio emission at 650 kilometers per second is associated, almost without exception, with a coronal mass ejection in the bulk velocity range of 400 to 1200 kilometers per second. Such ejections are easy to detect in modern coronagraph imagery. We have multiple coronagraphs in operation right now. The large angle and spectrometric coronagraph instruments aboard the Solar and Heliospheric Observatory, the COR2 instrument aboard Stereo A, and the relatively new compact coronagraph aboard the Geostationary Operational Environmental Satellites, designated CCOR1. Between them, these instruments provide near-continuous coverage of the corona around the Sun in multiple geometric perspectives. Yet the SWPC discussion at 12:30 Universal Time today, before today's flare, stated that no Earth-directed coronal mass ejections had been observed in available coronagraph imagery. After today's flare, the Eastern-directed coronal mass ejection should be visible in the post-flare frames, as it moves outward away from the Sun's eastern limb. The afternoon update will tell us its angular width, its bulk velocity, and its trajectory. If the angular width is unusually large, the trajectory could include an Earth-glancing component, even from this far east of central meridian. Most limb coronal mass ejections have angular widths of 30 to 60 degrees and stay confined to the launch hemisphere. A small percentage have angular widths of more than 90 degrees and can produce surprise-glancing impacts at Earth, even from limb sources. We won't know which category today's coronal mass ejection falls into until the next coronagraph analysis is published. Until then, the trajectory remains technically open. The fourth observation, which isn't really an anomaly, but more of a pattern recognition exercise, is that today's flare came from heliographic latitude north 18. That's the same latitude band as the May 7th M 2.6. It's also the same latitude band as the May 4th M 1.8, from north 17, west 80. 3 M-class flares in 7 days, all from the same north 17 to 21 latitude band. That could be a coincidence. Or it could be what solar physicists call an active longitude, a magnetically active band on the sun's surface that produces multiple regions over successive rotations. Active longitudes have been documented throughout multiple solar cycles. They tend to persist for several years. If we're looking at an active longitude in the north 17 to 21 band right now, we should expect continued elevated activity from that latitude over the coming months, regardless of which specific region produces it. That's not a forecast. That's a hypothesis worth testing against the data over the next several rotations. Whenever the sun does something dramatic, 3 predictable categories of speculation appear within hours, and it's worth running through each one cleanly so you can recognize the pattern when you encounter it elsewhere. I'm going to give each one its fair hearing, and then I'm going to tell you what the evidence actually says. The first claim that always appears is that NOAA is hiding the real threat. The argument runs something like this. NOAA's morning forecast described AR 4432 as the primary driver of elevated R3 blackout probabilities. NOAA didn't mention the new region. Therefore, NOAA either didn't know about it, which would be incompetence, or knew about it and chose not to disclose it, which would be concealment. The reality is much simpler than either of those interpretations. NOAA's 1230 Universal Time Forecast was issued before the 1319 Universal Time Flare. The forecast that mentioned AR 4432 was the morning bulletin, written when the new region had not yet erupted strongly enough to draw operational attention. Within minutes of the flare beginning, NOAA published 4 real-time alerts. The radio blackout alert ALTXMF at 1338, the Type 2 alert ALTTP2 at 1347, the 10 centimeter burst alert, SUM 10R at 1355, and the M5 summary, SUM XM5 at 1414. All 4 alerts are publicly accessible. The afternoon forecast revision will incorporate the new region. NOAA's forecast cadence is a matter of operational schedule, not concealment. The information is public. The agency publishes everything it observes in near real time. The argument that NOAA is hiding anything fails on basic sequencing. The second claim that always appears is that the High Frequency Active Auroral Research Program, HAARP, is responsible for solar activity. This claim has a remarkable persistence in the conspiracy ecosystem despite being mathematically impossible. Let me show you the math. HAARP transmits radio frequency energy at a maximum power of approximately 3.6 megawatts. If HAARP operated at full power for an entire 24-hour period, the total energy deposited into Earth's upper atmosphere would be approximately 3 times 10 to the 11th power joules. That's 300 billion joules. Today's M5.7 flare released a total energy of approximately 1 times 10 to the 25th power joules. That's 10 septillion joules. The ratio between the flare's energy and HAARP's daily output is approximately 14 orders of magnitude. The flare released, in 43 minutes, more than 100 trillion times the energy that HAARP could deposit in 24 hours. There is no physical mechanism by which an Earth-based ionospheric heater can modulate magnetic reconnection occurring in the corona of a star located 93 million miles away. The argument fails not because the people making it are dishonest, but because the energy budget makes the claimed mechanism impossible. The sun is so much bigger and more energetic than human technology that no human technology could modulate it even slightly. The third claim is more interesting because it has a kernel of legitimate observation embedded in incorrect framing. The claim is that mainstream media is deliberately suppressing coverage of solar activity. The legitimate observation underneath this claim is that Solar Cycle 25 has genuinely overperformed NOAA's official prediction, and that mainstream coverage of solar activity has been intermittent and frequently underplayed compared to other natural hazard categories. Both of those observations are factually accurate. Solar Cycle 25 did exceed predictions. Mainstream media coverage is uneven. The error in the conspiracy framing is the leap from underplayed to suppressed. Suppression implies an active mechanism, editors choosing to not run stories, government agencies choosing to not publish data, scientists choosing to not communicate findings. The actual situation is much simpler. SWPC publishes alerts in real time. NASA's database of notifications, knowledge, and information catalogs every flare and coronal mass ejection within hours of detection. The Wilcox Solar Observatory has continuously published polar magnetic field data since 1976. The information is there for anyone who looks for it. The reason mainstream media doesn't run more solar coverage is editorial story selection, not censorship. Editors prioritize stories with clear human consequences and visible imagery. Solar storms produce neither, most of the time. The right reframe of the criticism is that the public-facing communication infrastructure for solar storms is excellent at the technical level and uneven at the lay audience level. That's a fixable communication problem, not a conspiracy. There's a fourth angle that's worth flagging respectfully because it appears in genuine good faith pattern recognition. People notice that major solar events seem to cluster with other major events. Earthquakes, severe weather, volcanic eruptions, geopolitical crises. Today is a good example. The May 10th flare arrives during a major heat dome over the western United States. Ongoing fire weather across the northern plains, continued eruptive activity at the Mayon volcano in the Philippines, multiple moderate earthquakes across the Pacific Ring of Fire, and a developing flood event across Mississippi and Louisiana. The everything is happening at once sensation is real. It's not imagined, but the explanation isn't a coordinating cause. The sun runs on an 11-year cycle. Earth runs on a 1-year seasonal cycle. The Pacific Ring of Fire produces earthquakes on a roughly steady-state seismic budget. The atmospheric circulation runs on its own multi-week patterns. These are independent clocks, each ticking at its own rate, and any given week will produce some clustering of events purely by statistical accident. Pattern recognition is a virtue. Pattern fabrication is a trap. The challenge is staying on the right side of that line, and the test is whether you can articulate why two patterns are causally connected, not just observationally correlated. The Marchitelli framework, published in 2020 in the journal Scientific Reports by Marchitelli and colleagues, provides one of the more rigorous tests of solar seismic correlation. It identifies a statistical association between high solar wind, proton density, and magnitude 5.6 and greater earthquakes under specific solar wind conditions. The framework requires elevated proton density, specific magnetic field orientations, and a temporal correlation window that opens during solar wind impacts on Earth's magnetosphere. Today's space weather environment does not satisfy any of those conditions. Solar wind speed is moderate at 400 kilometers per second. The magnetic field strength is in the gentle 2 to 4 nanotesla range. The B's component is near neutral. There is no elevated proton flux. No coronal mass ejection has impacted Earth. Under the Marcatelli framework, today is a null condition. Any earthquake that occurs in the next 48 hours is not statistically attributable to today's flare. That doesn't mean an earthquake won't happen. Earthquakes happen every day. It means that if one does happen, you can't blame the sun. The mechanism isn't satisfied. The next 2 weeks are the actual story. Today's flare is the entry point, but it's not the headline. The headline gets written between now and approximately May 24th, depending on what the new region does as it rotates across the visible disk. Here's what to watch for, and here's why each indicator matters. The first thing to watch for is the next flare from the same region. If the new region produces another M-class flare within 48 hours of today's event, that's a strong indicator that we're in Story 2 or Story 3. Active growth or late cycle farside surge. A second flare in 48 hours would mean the region is either still growing or operating at a high baseline of complexity, both of which raise the probability of an X-class event during the central meridian window. If the region goes quiet for several days, that's a strong indicator that we're in Story 1, routine emergence. The M5.7 would represent the region's current ceiling, and the next 2 weeks would consist of moderate background activity rather than escalating threats. The second thing to watch for is the magnetic complexity assessment that NOAA will publish over the coming days. As the region rotates further into view, NOAA will be able to characterize its sunspot count, its Macintosh classification, and its magnetic class. If the region develops into beta gamma, the same class as AR4432, that's a moderate alarm. If it develops into beta gamma delta, the most flare-productive class with mixed polarity sunspots in close proximity to each other, that's a serious alarm. Beta gamma delta regions produce X-class flares at significantly higher rates than other classifications. The Carrington event of 1859, the largest geomagnetic storm in recorded history, was produced by a beta gamma delta region with an estimated sunspot area of around 2,300 millionths. AR4432, for context, has 430 millionths, about 19% of Carrington's area. We don't know yet what the new region's area will turn out to be. If it's comparable to AR4432 or larger, and if it develops delta spot complexity, the threat profile during its central meridian window becomes elevated. The third thing to watch for is the behavior of AR4432 during its remaining geo-effective days. As I mentioned earlier, AR4432 carries a 5% published X-class daily probability that's likely closer to 10 or 15% in reality. The region has roughly 4 to 5 days left before it rotates off the western limb. If it produces an X-class flare during those 4 days, we get an Earth-impacting event from a known region while everyone's attention is shifting to the new arrival on the eastern limb. If AR4432 stays quiet through its final days, we exit the wildcard phase and transition fully into the new region watch. The fourth thing to watch for is what happens during the overlap window in mid-May. Around May 15th through May 17th, both regions will be simultaneously in geo-effective range. AR4432 will be in its final days at the western limb. The new region will be approaching central meridian. During those 3 days, both regions are theoretically capable of producing Earth-impacting flares. The probability of any single major event during those 3 days is the sum of each region's individual probability, which is meaningfully higher than either region alone. The overlap window is the highest risk segment of the next 2 weeks. The fifth thing to watch for, and the one that's hardest to communicate but maybe the most important, is the emergence of additional farside regions. If we're in Story 3, the late cycle farside surge interpretation, we should expect to see additional unfamiliar regions rotating into Earth view over the next several weeks, each one providing the same kind of opening shot moment we got today. If a second previously unknown region rotates around the eastern limb and produces a major flare within the next 10 days, the Story 3 hypothesis gets significantly stronger. If no further surprise regions appear, Story 3 weakens, and we're more likely in Story 1 or Story 2 for this specific region. The pattern of next rotation arrivals is the longest time scale indicator we have, and it's the indicator that determines whether the May 10th event is an isolated event or a representative example of an ongoing dynamic. There are a few things that don't matter as much as they sound like they should matter, and it's worth noting them so you know not to overweight them. The exact morning KP index over the next several days doesn't matter much for this story, because the geomagnetic field is downstream of solar activity, not predictive of it. A quiet KP doesn't mean the sun is quiet. A quiet KP means the sun's recent output hasn't reached us yet. The aurora forecast also doesn't matter much, for the same reason. Aurora is the visible consequence of geomagnetic disturbance, which is the visible consequence of solar wind impact, which is the lagging indicator of solar surface activity. Whatever's happening on the sun today won't show up in aurora reports for another 1 to 4 days, depending on whether the next event is Earth-directed and how fast its coronal mass ejection moves. By the time the aurora forecast updates dramatically, we'll already know what happened. The leading indicator is the X-ray flux and the active region monitoring, and those are what to watch. There's a seasonal context that's worth pausing on briefly. The Russell-McFerrin effect, named after Christopher Russell and Robert McFerrin in their 1973 paper in the Journal of Geophysical Research, describes a seasonal modulation of geomagnetic storm efficiency. The effect arises from the geometric alignment between the interplanetary magnetic field and Earth's magnetic dipole. Storms are most efficient near the equinoxes, late March and late September, and least efficient near the solstices. May 10th falls roughly 50 days after the spring equinox, in the seasonally declining phase of vernal equinox enhancement. A coronal mass ejection arriving at Earth on May 10th produces approximately 60% of the geomagnetic disturbance that the same coronal mass ejection would produce on March 21st. The new region's central meridian window in mid to late May falls during a period when geomagnetic efficiency is around 50 to 55% of equinox peak. That's a partial blunt on whatever the region produces. It doesn't mean we're safe. It means whatever the region does produces a smaller geomagnetic event than the same physical disturbance would produce in March or September. It's a small grace, and it's worth knowing. Let me end with the question I want you sitting with after the screen goes dark. The question isn't whether the new region is going to produce an X-class flare. The probability of that happening over the next 2 weeks is meaningfully above zero, but well below certain. The question isn't whether AR4432 is going to produce one final outburst before it disappears. That probability is also above zero and below certain. The question isn't whether either region is going to produce an Earth-directed coronal mass ejection during its central meridian window. That probability depends on the trajectory of whatever they launch and on factors we won't be able to assess until they launch it. The question, the actual question, is how many active regions are growing on the far side right now that we will only see once they've already started erupting? Think about that for a minute. The sun rotates once every 27 days. That means roughly half the surface area of the sun is hidden from Earth-based observation at any given moment. The rate of new region emergence isn't zero. New regions are appearing constantly, growing constantly, changing complexity constantly. We can detect the larger ones via helioseismic imaging, but the technique has resolution limits and latency limits. There is, at any moment, some unknown number of regions on the far side that we either don't see at all or see only as low-resolution helioseismic blobs. Some fraction of those regions are growing into significant complexity. Some fraction of that fraction will rotate into Earth view over the coming several rotations. Some smaller fraction of those will produce major flares during their central meridian windows. Today, one of those regions revealed itself. We don't know what it was doing during the 2 weeks before we saw it. We know it wasn't doing nothing, because a region capable of producing an M5.7 on its third day of visibility didn't just appear from nothing during those 3 days. It was already there. It was already loaded with magnetic complexity. We just couldn't see it. And the only reason we know about it now is because it announced itself by punching a hole in the morning forecast. How many other regions are doing the same thing right now? We don't know. We can't know. We have the best space weather monitoring infrastructure in human history, and there's a fundamental geometric limitation that we can't engineer our way past. We can observe what's facing us. We can't fully observe what's not. We can guess about what's not facing us based on indirect measurements. But guessing is not seeing, and the difference between those two things is the entire reason today's flare came as a surprise. This isn't a conspiracy story. It's a geometry story. It's a humbling one. We tend to think of the sun as a continuously monitored object, and at the level of its observable hemisphere, it is. But the sun is half monitored, by definition, because it has two hemispheres, and we can only see one of them at a time. The hemisphere we can't see is producing magnetic activity that we can only assess after the fact, when it rotates into our view. We are perpetually catching up. We are perpetually seeing the past of half the star. The May 10th flare matters not because of what it did to Earth today, which was a relatively brief radio blackout and nothing more, but because of what it represents. It represents the latest instance of the sun reminding us that our forecasts are constructed from incomplete information. It represents a region that grew unobserved and then announced itself with a moderate eruption. It represents the opening of a 2-week window during which we will find out whether this region is the end of its own story or the beginning of a larger one. The worst that happens in the next 2 weeks could be nothing. The region could decay. AR4432 could rotate quietly off the western limb. The overlap window could pass without incident. The sun could go back to producing the steady background activity it's been producing for the last several months. That's the modal outcome. It's also possible. It's not unlikely. But the worst that happens in the next 2 weeks could also be an X-class flare from a region that, 24 hours ago, didn't appear in any forecast. It could be a coronal mass ejection that surprises operational forecasters with its angular width or trajectory. It could be the first indication that the late cycle plateau of solar cycle 25 is going to extend further than expected, with continued unforecasted activity rolling around from the far side every several weeks. Any of those things could happen. None of them is guaranteed. All of them are within the range of possibility opened by what we observe today. The closing thought I'll leave you with is that the sun keeps no calendar. It doesn't owe us a quiet 2 weeks because we're tired of the quiet 2 weeks not happening. It doesn't owe us a forecastable surface because we'd prefer one. It rotates at its own rate, produces magnetic structures on its own internal timescales, and reveals its hand only when the geometry forces a reveal. We watch, we measure, we try to extrapolate. And every so often, on a Sunday afternoon, a region we couldn't see decides we're going to see it now, and the forecast we were operating under becomes the forecast we were operating under 12 hours ago. The shockwave that just launched is real. The plasma cloud is moving outward through space at 1.5 million miles per hour. The region that produced it is rotating toward us, 1 degree at a time, 27 days for a full circle, 13.5 days for a full visible passage. We are inside the watch window now. We will be inside it until the region rotates off the western limb in late May. And the answer to the question, what does this region do next, is not yet written. The sun rotates. We watch. And the worst this time may very well be yet to come.